So I've got two integrals on the board here. You can imagine, you see that square root, you think trig substitution, and in fact, yeah, trig substitution is exactly what you want to do here. So what I want to do, make my triangle just real quick. It's going to be 1x, right, 1 minus x squared. So sine theta is going to be x, and you can go ahead and do the this integral with this substitution. This integral you can also do with that substitution. If you want to do trig substitution, you can do this integral that way. Notice though that this one has an even power x squared up here, but this one has an odd power x to the fifth up here. In this one though, we have an alternative, which won't work here because there's not the du. So here we're stuck even power square root, trig sub all the way. This guy, our choice is if we do instead do u being 1 minus x squared, then du is minus 2x dx, right? So what I can do, I wish I should not have done that way. Let me do it, let me put it up here. What I can do is break this up, x to the fourth, and then x dx over here, and then square root of 1 minus x squared. Then I got, this bottom is just square root of u. This is minus du, well this is du, and it'll have a minus 1/2, right, because it's minus 2 here. So this one goes to that. And then what am I going to do with this x to the fourth? I have to go back here, right? So if I've got x squared equals 1 minus u, then x to the fourth is going to be 1 minus u quantity squared. So I also do have the option, because of this power, of doing this way, right? And then what is this? I work out this top, right? It's 1 minus 2u plus u squared, and each of these is over a square root of u. So these are all kind of straightforward, u to the 3/2, u to the 1/2, whatever, right? So these now are easy power rules. If we had done this with this, oh, you would probably see you would have a sine to the fifth, so it would be kind of a mess. But maybe the integral wouldn't be that bad. Anyway, you'd end up with the same answer in the end. All right, so that's that. But I have more. So let's see. Another example. Natural log of 1 plus x squared dx. Well, this is one where you're like, well, I don't have much choice here, right? Because there's nothing that I can use. I can't use u equals 1 plus x squared because there's no du. I can't do this, I can't do that. I'm basically stuck here with integration by parts, which is often going to be the case when it's just natural log by itself or inverse tan or whatever by itself. You're just stuck. So v equals x, and then what's my du? du is going to be 1 over 1 plus x squared, but derivative of that, so 2x, chain rule, right? So then this gives me this, and then this gives me this. Okay, so this isn't super great either. I mean, it's not awful, but it's not super great because I've got x squared. Again, I do have a rational function, but I've got the same power on top and bottom, so I have to do my little thing where I can, divide. Right, let me put this 2 out here for a moment. So I can divide I'm going to show you, though, there's a trick that you can use with probably most of these. You can always do long division. If you don't see it, it's fine. But if you see it, you can actually, you know, make your life a little bit easier. Because what is this? This is x squared over x squared plus 1. I can write it either way, right? So notice I'm really close. They're really close, right? So I can do plus 1 minus 1, right? Plus 1 minus 1 is 0. So x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. So sometimes I can rearrange sort of with a clever little trick. Now, this, of course, is easy because it's just x minus inverse tan. But notice that I needed to do something. So if I see something like this, you can go ahead and do something like that. Of course, if you didn't see it, you could definitely do x squared divide by 1 plus x squared, and it's 1 minus minus, and you get minus 1. You get the same thing, right? So you can always do long division, but if you don't want to do long division and you see something simple that you can recognize like that, you can absolutely go and do that as well. Alrighty, 4 or 5. I have so many of these, you guys. I could do these all day. All right, let's see. Here's a couple more. This one should look familiar to you because we did something like this on a worksheet. You can kind of see the same thing, right? You want to let u be e to the x. Then du is e to the x dx. Notice you've got, though, e to the 2x in the top here. So I just wanted to kind of point that out. You do have to figure out the best way to use your substitution, right? Because you might want to put e, you might be tempted to just say u squared in the top, but then you don't have the dx. So you really have to think about the dx when you're doing these and make sure that you've substituted everything you can, right? This is times this, and this is 1 plus e to the x. So really, when I substitute these in, I do want to be a little bit careful so I end up with the right thing. It's easy to sort of forget the dx and then you get the wrong answer. So then I have this, and again, I can do either way. I can divide out, or I can do what I did in that previous example, right? Because I can do u over 1 plus u is u plus 1 minus 1 over 1 plus u, right? So they're the same. So I have 1 minus 1 over 1 plus u. And then this is a straightforward kind of integral. Do both of those and put back the x. Okay. Here's a cute it's a cute one. Theta inverse tan of theta. Actually, this is a really easy integral. If you, no, not that. I'm like, I don't want inverse tan. So if it was inverse tan, by the way, what would I do? I would have to do integration by parts, and then it would be ugly. But no, we can do that. We can do that one next. All right, so let's do this. This one's much nicer. Okay, so if I've got this, right, what I want to do is do this integral. And again, this is also going to be an integration by parts. It's got to be the first thing to try because you've got theta times something which is a, trig function. So you've got sort of like two different kinds of functions. So integration by parts makes sense. But if I sort of, and this is a thing that you should do, by the way, when you're thinking about like classifying the integral and what is going to be my strategy. If you're going to use integration by parts before you start barreling through, give it a little thought, right? So if I did u equals theta, and dv is the rest of the stuff, which is sort of the standard thing that we do when we do like x sine x or whatever. This is a big problem, right? Because I then have to find the antiderivative of this, but that's not that's not like a normal antiderivative from the from our chart. Tangent squared isn't, but secant squared is. So sort of thinking about that kind of gets you to an idea that maybe what I should do before I do this is do sort of some pre-processing, right? So we know that tangent squared plus 1 is secant squared. So what if I do theta, and here I'm going to call this secant squared minus 1, right? So now I end up with two integrals, theta secant squared theta minus theta, right? So this is d theta and this is d theta, right? Yeah. So this one's easy. This one is still an integration by parts, but it's not a hard integration by parts now, because if I do this, if dv is secant squared theta, then v is going to be tangent, du is just going to be d theta. So I'm going to have theta tangent theta. All right, I'm just going to write it. Theta times tangent of theta minus the integral of tan theta d theta, and then whatever this was. Theta squared root of 2, right? So, and this one is just, you remember how to do that one. You write a sine over cosine and it's natural log of cosine. So, just sort of by doing a little bit sort of this, it becomes easier to deal with.